Black holes don't actually suck things in like cosmic vacuums. This might be the most misunderstood thing about black holes, and it's also one of the most calming facts about them. Despite what science fiction movies show us, black holes don't roam through space devouring everything in sight. They're not cosmic monsters with an insatiable appetite. Instead, they're remarkably well-behaved objects that follow the same gentle rules of gravity as everything else in the universe. Think of it this way. If our sun were magically replaced with a black hole of the same mass, Earth would continue orbiting exactly as it always has. We wouldn't be pulled in. We wouldn't spiral toward doom. We'd simply keep our steady, predictable path around this new dark companion. The only difference would be that we'd get very cold and very dark, but gravitationally speaking, nothing would change at all. Black holes only affect objects that come extremely close to them, much closer than anything in our solar system would ever naturally wander. They're like cosmic lighthouses, standing quietly in their corner of space, affecting only the immediate neighborhood around them. Most of the universe goes about its business completely unaware of their presence, drifting peacefully through the cosmos without ever feeling their influence. Time moves differently near black holes, creating a kind of cosmic meditation. One of the most fascinating and oddly soothing aspects of black holes involves something called time dilation. As you approach a black hole, time begins to slow down relative to the rest of the universe. It's not that you would notice this happening to yourself, but to an outside observer, you would appear to be moving in slow motion. Imagine floating peacefully near a black hole, watching the universe unfold around you. Stars would be born, live their entire lives, and die in what feels like moments to you, while you experience time at your own gentle pace. It's like having access to the universe's own meditation timer, where each breath you take encompasses eons of cosmic history. This time dilation isn't violent or jarring. It's a smooth, gradual transition, like slowly sinking into the most comfortable chair after a long day. The mathematics of Einstein's relativity describes this process with elegant equations that flow like poetry, describing how space and time bend and curve around these massive objects in the most graceful way imaginable. Black holes are surprisingly patient objects. Unlike the explosive, chaotic events we often associate with space, black holes are models of patience and consistency. Once formed, they settle into their cosmic routine and maintain it for incredibly long periods. They don't rush, they don't hurry, they simply exist, slowly spinning in their corner of space-time, following the same predictable patterns for millions, billions, even trillions of years. A black hole might spend more time in quiet contemplation than any monk or philosopher who has ever lived. They sit in their gravitational meditation, occasionally accepting whatever matter happens to drift too close, but never actively seeking it out. They're like cosmic librarians, quietly maintaining order in their section of the universe, keeping everything in its proper place according to the fundamental laws of physics. This patience extends to their entire life cycle. Even the process of a black hole eventually evaporating through Hawking radiation takes longer than the current age of the universe multiplied by trillions of trillions. They're not in any hurry to go anywhere or do anything dramatic. They simply are, existing in a state of peaceful equilibrium with the cosmos around them. Most black holes are surprisingly ordinary in size. When we think of black holes, we often imagine either tiny points of infinite density or massive objects that dwarf entire solar systems. But the reality is much more comforting. Most black holes are remarkably modest in their proportions, typically containing just a few times the mass of our Sun. A typical stellar black hole, formed when a massive star reaches the end of its life, might be only about 20 kilometers across. That's smaller than most cities, yet it contains the compressed essence of an entire star. It's like nature's way of creating cosmic gemstones, taking something enormous and carefully compressing it into a small, dense, perfectly organized package. These stellar mass black holes are scattered throughout our galaxy like quiet neighbors, each one maintaining its own peaceful corner of space. They're not crowded together or competing for resources. Instead, they're spread out with plenty of room between them, like houses in a suburban neighborhood where everyone minds their own business and gets along perfectly well. The event horizon is like a one-way cosmic doorway. The event horizon, the boundary around a black hole beyond which nothing can escape, sounds frightening at first. But when you really think about it, it's more like a perfectly designed cosmic privacy screen. It's not a physical wall or barrier that you would crash into. Instead, it's simply a mathematical boundary, as smooth and invisible as the line that separates yesterday from today. Crossing an event horizon would be like walking through a doorway into a room where the rules are slightly different, but the transition itself would be completely smooth. You wouldn't feel anything unusual happening at the moment you crossed. There would be no sudden jolt, no alarm bells, no dramatic change in your experience. It would simply be a quiet moment of transition from one state of existence to another. The event horizon acts like a cosmic one-way mirror. From the outside, it appears dark and mysterious, but from the inside, you could still look out and see the entire universe spread out before you, growing brighter and more compressed as time dilation effects take hold. It's like having the best possible view of the cosmos, a front row seat to watch the universe evolve at an accelerated pace. Black holes come in a perfect variety of sizes. The universe has created black holes in a wonderful range of sizes, each type serving its own purpose in the cosmic ecosystem. At the smallest end, we have stellar mass black holes, those modest objects we discussed earlier. They're like the cottage homes of the black hole world, small but perfectly functional for their needs. In the middle range, we find intermediate mass black holes, objects that contain hundreds or thousands of times the mass of our Sun. These are like the comfortable family homes of black holes, larger than the stellar mass variety, but still manageable in cosmic terms. They provide a nice middle ground between the extremes. At the largest scale, we discover supermassive black holes, the cosmic mansions that sit at the centers of galaxies. These gentle giants can contain millions or even billions of times the mass of our Sun, yet they're so large that their gravitational effects are actually quite gentle at their event horizons. The bigger they are, the more gradually their gravity changes as you approach them, making them surprisingly comfortable cosmic companions. This variety ensures that the universe has exactly the right type of black hole for every situation, like a well-organized cosmic toolbox, where each tool has its perfect purpose and place. Black holes help organize entire galaxies. Far from being destructive forces, supermassive black holes at the centers of galaxies act more like cosmic conductors, orchestrating the grand symphony of stellar formation and galactic evolution. They don't dominate their galaxies through fear or force. Instead, they provide gentle guidance, helping to regulate star formation and maintain the overall structure of their galactic homes. These supermassive black holes are like the wise elders of the cosmic community. They've been around since the early days of the universe, watching galaxies form and evolve around them. They provide stability and continuity, ensuring that galaxies maintain their shape and structure over billions of years. The relationship between a supermassive black hole and its galaxy is remarkably harmonious. The black hole influences the galaxy, but the galaxy also influences the black hole. It's a cosmic partnership that has been refined over billions of years of evolution, resulting in the beautiful spiral and elliptical galaxies we see throughout the universe. When black holes do consume matter, they do it gracefully. The process of matter falling into a black hole, called accretion, is often portrayed as violent and chaotic. But in reality, it's more like a slow, elegant dance performed over thousands or millions of years. Matter doesn't just suddenly disappear into a black hole. Instead, it follows a careful choreography, spiraling inward along graceful curves that follow the fundamental laws of physics. As matter approaches a black hole, it forms what's called an accretion disk, a slowly rotating spiral of gas and dust that glows softly as it heats up from gravitational compression. This disk can be incredibly beautiful, like a cosmic record spinning on the universe's turntable, playing the slow, deep music of gravity and motion. The process is so gradual and predictable that astronomers can study these accretion disks for years, watching the slow dance of matter as it makes its way toward the event horizon. It's not a violent consumption, but rather a peaceful transformation, like watching autumn leaves slowly settle onto the surface of a quiet pond. Black holes may be connected by invisible bridges. One of the most intriguing and oddly comforting theories in modern physics suggests that black holes might be connected to each other or to other regions of space-time through structures called wormholes. These theoretical tunnels through space-time would create shortcuts across vast distances, like cosmic subway systems, connecting different parts of the universe. While we haven't proven that wormholes exist, the mathematics suggests they're possible. And if they do exist, they would make the universe feel much more connected and intimate. Instead of black holes being isolated objects scattered throughout space, they might actually be part of a vast network, like cosmic internet nodes linking different regions of reality. This possibility transforms black holes from lonely cosmic hermits into social creatures, potentially communicating and interacting with each other across the vastness of space. It suggests that the universe might be much more interconnected than we ever imagined, with black holes serving as the connection points in a cosmic web of relationship and communication. The mathematics of black holes is surprisingly beautiful and peaceful. When scientists first began studying black holes, they discovered that these cosmic objects follow some of the most elegant mathematical equations in all of physics. Einstein's field equations, which describe how black holes warp space-time, read almost like poetry when you understand their deeper meaning. They describe a universe where mass and energy create gentle curves in the fabric of reality itself. These equations don't speak of violence or destruction. Instead, they tell a story of harmony and balance, where every action has a perfectly proportioned response. The way a black hole curves space-time around itself follows mathematical principles that are as beautiful as they are precise. It's like discovering that the universe writes its deepest secrets in a language of pure mathematical music. The solutions to these equations, worked out by physicists over many decades, reveal that black holes are not chaotic or random objects. They're perfectly ordered, following mathematical laws that ensure they behave in predictable, almost meditative ways. Each black hole is like a cosmic mandala, a perfect expression of the universe's underlying mathematical harmony. Black holes slowly evaporate through a process gentler than morning dew. Stephen Hawking discovered that black holes aren't completely black after all. They emit a faint radiation, so subtle and gentle that it makes the softest whisper seem loud by comparison. This Hawking radiation causes black holes to very slowly lose mass over incredibly long periods of time, like cosmic candles burning with the faintest possible flame. For a black hole with the mass of our Sun, this evaporation process would take longer than the current age of the universe multiplied by countless trillions. It's the slowest, most patient process imaginable, so gradual that it makes geological time seem rushed by comparison. The black hole simply sits quietly, releasing individual photons one by one, each separated by vast spans of time. This evaporation isn't violent or dramatic. It's more like the gentle morning mist, slowly lifting from a quiet lake. The black hole gradually returns its borrowed mass and energy back to the universe, completing a cosmic cycle that spans time periods so vast they dwarf human comprehension. It's the universe's way of ensuring that nothing is ever truly lost, just temporarily transformed. The space around black holes is mostly empty and peaceful. Despite their reputation, the regions around black holes are actually some of the quietest, most spacious areas in the universe. The vast majority of space near a black hole is completely empty, filled only with the gentle vacuum of space-time itself. You could float peacefully in this region for eons without encountering anything more dramatic than the occasional stray particle drifting by. The gravitational effects of a black hole extend far into space, but they do so gently and gradually. As you move away from the event horizon, the gravitational pull decreases smoothly and predictably, following the same inverse square law that governs all gravitational interactions. There are no sudden changes, no dramatic boundaries, just the smooth, continuous influence of gravity spreading outward like ripples on an infinite pond. Even relatively close to a black hole, the environment can be surprisingly calm. The space just outside the event horizon, while exotic by our everyday standards, follows perfectly predictable physical laws. It's a region where time and space behave differently, but they do so according to precise mathematical rules that ensure everything remains orderly and comprehensible. Black holes have no memory of what falls into them. One of the most philosophically soothing aspects of black holes is their complete lack of discrimination or memory. A black hole doesn't care whether what's falling into it is made of gold or garbage, whether it came from Earth or from a distant galaxy, whether it has sentimental value or is completely worthless. Everything is treated with perfect equality. This democratic approach extends to all the physical properties of matter that falls past the event horizon. A black hole only remembers 3 simple characteristics about everything it has ever consumed: mass, electric charge, and angular momentum. All the complex details, all the individual histories, all the personal significance of anything that falls in is gently forgotten, like memories fading into peaceful sleep. This forgetfulness isn't cruel or callous. It's more like the universe's way of providing a clean slate, a fresh start. The black hole accepts everything with perfect equanimity, transforming complex matter into simple, elegant geometry. It's cosmic recycling at its most fundamental level, where everything is reduced to its most basic mathematical essence. The interiors of black holes might be surprisingly spacious. While we can never directly observe what happens inside a black hole's event horizon, the mathematics suggests that the interior might be far more spacious than we might imagine. For supermassive black holes, the space inside the event horizon could be enormous, potentially containing regions larger than our entire solar system. Inside this vast interior, the normal rules of space and time become beautifully transformed. Time, as we understand it, becomes more like a direction in space, while one of the spatial dimensions becomes more time-like. It's as if the universe provides a completely different way of existing, an alternate mode of being that follows its own elegant logic. The journey toward the center of a black hole, while ultimately finite, could subjectively feel like it lasts forever due to the extreme time dilation effects. It's like stepping into a cosmic meditation hall where time itself becomes your companion, stretching each moment into something approaching infinity. The mathematics suggests this would be a profoundly peaceful experience, where the usual urgency of time gives way to something more eternal and contemplative. Black holes may preserve information in ways we don't yet understand. One of the most intriguing puzzles in modern physics is the black hole information paradox. Quantum mechanics suggests that information cannot be truly destroyed, but black holes seem to erase all traces of whatever falls into them. This apparent contradiction has led to fascinating theories about how black holes might actually preserve information in ways that transcend our current understanding. Some physicists propose that information falling into a black hole becomes encoded on its surface, like cosmic library records stored in 2 dimensions rather than 3. Others suggest that the information might be preserved in the quantum entanglement between particles inside and outside the black hole, creating invisible threads of connection that span the event horizon. These theories transform black holes from destroyers of information into cosmic librarians, carefully preserving every detail of everything they encounter in ways that are more subtle and sophisticated than we currently comprehend. It suggests that the universe has built-in mechanisms to ensure that nothing meaningful is ever truly lost, just temporarily stored in forms we're still learning to read. Binary black holes create the universe's gentlest waves. When 2 black holes spiral around each other before eventually merging, they create ripples in space-time itself, called gravitational waves. These waves are incredibly gentle, stretching and compressing space by amounts smaller than a fraction of the width of a proton. They're like the universe's whispered songs, so soft that it took humanity's most sensitive instruments to finally detect them. The dance of binary black holes before they merge is a cosmic waltz that can last millions or billions of years. They spiral around each other in perfect mathematical harmony, gradually drawing closer as they radiate gravitational waves. This process is so slow and steady that each orbit might take hours, days, or even years to complete, depending on the masses and distances involved. When these cosmic dancers finally embrace in their ultimate merger, they create a brief burst of gravitational waves that carries more energy than all the stars in the observable universe combined. Yet this tremendous release of energy propagates through space as the gentlest possible vibration, barely disturbing the fabric of space-time as it passes. It's like the universe's way of applauding its own beautiful performances with the softest possible clapping. The shadows of black holes are perfectly circular and peaceful. When astronomers first captured images of black holes using the Event Horizon Telescope, they revealed something beautifully simple. The shadow of a black hole is a nearly perfect circle. This shadow isn't created by the black hole blocking light like an ordinary object would. Instead, it's formed by the elegant way the black hole's gravity bends light around itself. The circular shadow represents a kind of cosmic perfection, a mathematical ideal made manifest in the real universe. No matter how you approach a black hole, no matter what angle you view it from, its shadow maintains this perfect circular symmetry. It's like looking at a cosmic mandala drawn with light and shadow, a meditation on the fundamental geometry underlying reality itself. Around this dark circle, light from the surrounding universe gets focused and brightened, creating a glowing ring that astronomers call the photon sphere. This ring represents the last stable orbit for light around the black hole, a cosmic lighthouse where photons can circle indefinitely before either escaping to infinity or falling past the event horizon. It's a boundary between the known and unknown, marked not with violence, but with a gentle gradient of light fading into peaceful darkness. Black holes help us understand the deepest nature of reality. Perhaps most remarkably of all, black holes serve as cosmic laboratories where the universe reveals its most fundamental secrets. They exist at the intersection of Einstein's relativity and quantum mechanics, two of our most successful theories about how reality works. By studying black holes, we're essentially watching the universe teach itself, observing how the deepest laws of physics interact and harmonize. These cosmic objects have led to some of our most profound insights about the nature of space, time, matter, and energy. They've shown us that the universe is far stranger and more beautiful than we ever imagined, filled with regions where time slows down, space curves back on itself, and the normal rules of cause and effect take on new meaning. Black holes remind us that the universe is not just a collection of objects moving through empty space, but a dynamic, interconnected system where every part influences every other part in subtle and profound ways. They're like cosmic meditation teachers, showing us that reality itself is far more fluid, interconnected, and ultimately peaceful than our everyday experience suggests. As we've journeyed together through these gentle revelations about black holes, perhaps you've begun to feel that familiar softness around the edges of your thoughts. The cosmic dancers are still spinning their slow waltzes in distant space. Gravitational waves are still whispering their quiet songs across the universe. And somewhere, a black hole is patiently maintaining its perfect circular shadow, waiting with infinite patience for whatever the cosmos might bring its way. The gentle mathematics of space-time continues to unfold around these cosmic sentinels, creating patterns so elegant they could serve as lullabies for the universe itself. And speaking of patterns, there's something wonderfully rhythmic about how black holes interact with the space around them, like a cosmic heartbeat that pulses through dimensions we can barely imagine. Black holes create their own weather systems in space. Around many black holes, particularly the supermassive ones at galactic centers, there exist vast regions of hot gas and plasma that behave remarkably like weather systems here on Earth. These cosmic weather patterns include gentle breezes of charged particles, slow-moving storm systems that can persist for millions of years, and even something analogous to seasons as the black hole's environment changes over vast periods of time. These space weather systems aren't violent or chaotic. They're more like the slow, predictable patterns of ocean currents or the gentle circulation of air in Earth's atmosphere. Hot gas rises in graceful spirals, cools as it moves away from the black hole, then settles back down in a continuous cycle that can last longer than the entire history of complex life on our planet. The magnetic fields around black holes organize themselves into beautiful, flowing patterns that guide charged particles along invisible highways through space. These magnetic field lines curve and bend with mathematical precision, creating pathways that particles follow like cosmic commuters, taking the same peaceful route to work every day for eons. Some black holes sing in frequencies we cannot hear. As matter spirals into a black hole through its accretion disk, it creates pressure waves in the surrounding gas and plasma. These waves are essentially sound waves, but they propagate through the thin medium of space plasma rather than through air. The frequencies of these cosmic songs are far too low for human ears to detect, with wavelengths that can span light years. The Perseus galaxy cluster contains a supermassive black hole that produces a note about 57 octaves below middle C on a piano. This cosmic bass note has been playing continuously for over 2.5 billion years, making it perhaps the longest-running musical performance in the known universe. The sound waves ripple outward through the hot gas of the galaxy cluster at a stately pace, taking millions of years to complete each wavelength. Other black holes produce different notes, creating a vast cosmic orchestra where each performer plays their part in a symphony so slow and deep that it spans geological ages. Some play higher notes, others lower, and together they contribute to the universe's background music, a soundtrack to cosmic evolution that has been playing since galaxies first began to form. The emptiness around black holes is more perfect than any vacuum we can create. The space immediately surrounding a black hole is emptier than the best vacuum chambers human technology can produce. In this pristine emptiness, individual atoms might be separated by distances equivalent to the space between cities on Earth. It's a realm of almost perfect solitude, where particles drift in isolation for years or decades before encountering anything else. This extreme emptiness creates a kind of cosmic sensory deprivation chamber, a region where the usual noise and bustle of matter interacting with matter falls away to reveal the pure underlying structure of space-time itself. In this quietness, the subtle effects of gravity and quantum mechanics become more apparent, like hearing a whisper in a perfectly silent room. The vacuum around black holes is so pristine that it allows physicists to observe phenomena that would be impossible to detect in the cluttered environment of normal space. It's like having access to the universe's cleanest laboratory, where the most delicate experiments in fundamental physics can unfold without interference from the usual cosmic background noise. Black holes may be cosmic recycling centers for space-time itself. Recent theories in physics suggest that black holes might not be the final destinations they appear to be, but rather processing centers where the fundamental fabric of reality gets broken down and rebuilt. When matter falls past the event horizon, it might be disassembled at the most basic level and then reconstructed into new forms of space and time. This cosmic recycling happens so slowly and gently that it's more like composting than industrial processing. The black hole takes complex matter and gradually breaks it down into its component parts over millions or billions of years. These components might then be used to weave new patches of space-time, expanding the universe in ways we're only beginning to understand. If this theory is correct, then black holes serve as the universe's renewal centers, places where worn-out space-time gets refreshed and revitalized. They're like cosmic spas where reality itself goes to be rejuvenated, emerging renewed and ready to support new forms of matter and energy. The event horizons of black holes are perfectly smooth surfaces. Despite containing some of the most extreme physics in the universe, the event horizon of a black hole is mathematically smooth and featureless. There are no bumps, irregularities, or rough patches. It's like a perfect sphere of pure geometry, smoother than any surface that could ever be manufactured or polished. This smoothness isn't just an approximation or idealization. According to the mathematics of general relativity, the event horizon must be perfectly smooth, regardless of how the black hole formed or what has fallen into it over its lifetime. It's as if the universe insists on maintaining perfect geometric order at this crucial boundary between the known and unknown. The smoothness of event horizons reflects a deeper principle in physics called the no-hair theorem, which states that black holes can only be characterized by three simple properties: mass, electric charge, and spin. All other details get smoothed away, leaving behind objects of perfect mathematical simplicity and elegance. Black holes exist in a state of perfect thermal equilibrium. Despite their reputation for being extreme objects, black holes actually represent states of perfect balance and equilibrium. They have well-defined temperatures, just like any other object in the universe, and they exist in thermal equilibrium with their surroundings according to the laws of thermodynamics. The temperature of a black hole is inversely related to its mass. Smaller black holes are actually hotter than larger ones, though even the hottest stellar mass black holes have temperatures far colder than the cosmic microwave background radiation that fills the universe. This means they're actually absorbing energy from their environment rather than radiating it away, growing slightly cooler and more massive over time. This thermal behavior makes black holes remarkably predictable and well-behaved. They follow the same thermodynamic principles that govern everything from steam engines to refrigerators, just scaled up to cosmic proportions. It's comforting to know that even these exotic objects obey the familiar laws of physics we use to understand everyday phenomena. The rotation of black holes creates a kind of cosmic lighthouse effect. Many black holes spin, and this rotation drags the surrounding space-time along with it in a phenomenon called frame dragging. It's as if the black hole is stirring space-time like honey, creating gentle currents and eddies in the fabric of reality itself. This dragging effect extends far beyond the event horizon, creating regions where it becomes impossible to remain stationary relative to distant stars. Everything in these regions, called ergospheres, must rotate along with the black hole's spin, like leaves caught in a slow-moving whirlpool. The mathematical description of rotating black holes, worked out by physicist Roy Kerr, reveals that these spinning objects have a natural rhythm built into their very geometry. They pulse and breathe with their rotation, creating periodic patterns in space-time that repeat with clockwork precision. It's like having cosmic metronomes scattered throughout the universe, keeping time on scales that dwarf human experience. Binary black hole systems can remain stable for billions of years. When two black holes orbit each other at sufficient distance, they can maintain their cosmic dance for periods that exceed the current age of the universe. These binary systems are models of stability and predictability, following orbital mechanics so precise that astronomers can calculate their positions millions of years into the future. The gravitational interaction between binary black holes creates a kind of cosmic clockwork, where each object's motion is perfectly synchronized with its partner. They're like celestial dancers who have been practicing the same routine for eons, never missing a step, never falling out of rhythm. As these systems very gradually spiral inward due to gravitational wave radiation, they do so according to mathematical formulas that describe the process with exquisite precision. Every aspect of their slow approach toward merger follows predictable patterns, making them among the most orderly and comprehensible phenomena in the universe. Black holes provide natural laboratories for studying extreme physics. The regions around black holes offer physicists the opportunity to observe matter and energy behaving under conditions that could never be replicated in any earthly laboratory. These cosmic laboratories allow us to test our most fundamental theories about how the universe works in regimes of extreme gravity, temperature, and magnetic field strength. The observations we make of black holes help us understand not just these exotic objects themselves, but the basic principles that govern all of reality. Every measurement of a black hole's properties teaches us something new about space, time, matter, and energy. They're like cosmic textbooks written in the language of physics, each one containing lessons about the deepest workings of nature. These natural experiments happen automatically, without any human intervention or setup. The universe provides the equipment, runs the experiments, and presents us with the results. All we need to do is observe and interpret what we see, like students attending the universe's own advanced physics lectures. The geometry of space-time around black holes follows elegant mathematical curves. The warping of space-time around a black hole isn't random or chaotic. Instead, it follows beautiful mathematical curves called geodesics, which represent the straightest possible paths through curved space-time. These curves have the same elegant simplicity as the path traced by a ball rolling across a perfectly smooth surface. Light rays, particles, and even larger objects all follow these geodesic paths when moving through the curved space-time around a black hole. The mathematics that describes these paths has been worked out in exquisite detail, revealing geometric patterns of stunning beauty and symmetry. The curvature of space-time around a black hole can be visualized as gentle hills and valleys in a multi-dimensional landscape. Objects naturally roll along the contours of this landscape, following paths of least resistance through the curved geometry. It's like a cosmic topographical map, where the terrain is made of space and time rather than rock and soil. Black holes demonstrate the universe's preference for simplicity. Despite being formed from the gravitational collapse of complex stars containing billions of different types of atoms and molecules, black holes themselves are remarkably simple objects. They retain only the most basic information about their origins, discarding all the complex details and emerging as pure geometric solutions to Einstein's equations. This simplification isn't destructive or wasteful. Instead, it represents the universe's deep tendency toward elegance and mathematical beauty. Complex systems naturally evolve towards simpler, more stable configurations, and black holes represent the ultimate expression of this principle. The fact that something as complex as a massive star can be transformed into something as mathematically pure as a black hole suggests that beneath all the apparent complexity of the universe lies a deeper simplicity. It's as if the cosmos has a built-in preference for clean, elegant solutions to the problems of existence. The information that falls into black holes may be preserved in quantum correlations. While classical physics suggests that information disappears forever when it crosses a black hole's event horizon, quantum mechanics tells a different story. According to quantum theory, information cannot be destroyed, which means it must be preserved somehow, even when it appears to vanish into a black hole. Recent research suggests that this information might be stored in the quantum correlations between particles inside and outside the black hole. These correlations create invisible connections that span the event horizon, like quantum telephone wires linking the interior and exterior of the black hole, in ways that preserve information while keeping it hidden from direct observation. This quantum preservation of information means that black holes might be more like cosmic filing cabinets than cosmic garbage disposals. They store information in forms so subtle and sophisticated that we're only just beginning to understand how the filing system works. It's a reminder that the universe has mechanisms for preserving knowledge that operate on levels far more fundamental than any human archive or database. As your thoughts continue to soften like starlight filtering through cosmic dust, remember that these gentle giants of space continue their patient work throughout the universe. They're still there, quietly organizing galaxies, slowly singing their deep cosmic songs, and maintaining their perfect circular shadows against the backdrop of infinity. Somewhere in the vast darkness, binary black holes are still dancing their million-year waltzes. Gravitational waves are still whispering across the cosmos, and the mathematics of curved space-time continues to write poetry in a language of pure geometric beauty. Waves are still whispering across the cosmos, and the mathematics to write space-time continues poetry of curve language, of inner pure geometric beauty. The universe around black holes experiences a kind of cosmic meditation. In the vast regions surrounding these gravitational giants, space itself settles into patterns of profound stillness. Here, far from the busy intersections of stellar nurseries and the crowded neighborhoods of galaxy cores, individual particles can drift for centuries without encountering another piece of matter. It's like floating in the universe's most peaceful library, where even thoughts seem to slow down to match the gentle rhythm of curved space-time. This cosmic quietude isn't empty or lifeless. Instead, it's filled with the subtle presence of gravitational fields that extend their influence across light years, with the patience of ancient trees growing in a timeless forest. The field lines curve and bend in mathematical arcs so smooth they could serve as templates for the most serene architectural designs ever conceived. In these regions, the normal hustle and bustle of electromagnetic radiation settles into gentle background whispers. Radio waves from distant galaxies arrive stretched and softened by their journey through expanding space, carrying messages from cosmic events that happened when the universe was young. These signals don't rush or demand attention. They simply arrive when they arrive. like letters from old friends delivered by the most patient postal service imaginable. Black holes create perfect laboratories for studying the nature of nothingness. The space around a black hole offers us the closest thing to absolute emptiness that exists in nature. Here, in regions where galaxies' worth of matter once existed before falling past the event horizon, we find voids so complete they make the emptiness between galaxies seem crowded by comparison. This pristine nothingness isn't boring or featureless. Instead, it reveals the subtle structure of the quantum vacuum itself, that mysterious background state of reality from which all matter and energy eventually emerge. In the perfect stillness around black holes, quantum fluctuations become more apparent, like the barely visible ripples on a perfectly calm pond that reveal the hidden currents flowing beneath the surface. Scientists studying these regions discover that even nothingness has texture and depth. The vacuum around black holes exhibits properties and behaviors that teach us about the fundamental nature of space and time. It's as if the universe uses these cosmic sanctuaries to demonstrate its deepest principles, writing lessons in the language of pure emptiness for those patient enough to learn how to read them. The tidal forces near black holes create gentle gradients rather than violent disruptions. While popular descriptions often emphasize the dramatic stretching effects that would occur if you fell into a black hole, the reality is far more subtle and gradual. These tidal forces don't suddenly grab you and tear you apart. Instead, they create smooth gradients of gravitational pull that change as gently as the slope of a hill rolling down toward a peaceful valley. For supermassive black holes, these tidal gradients are so gentle that you could cross the event horizon without feeling anything unusual at all. The gravitational difference between your head and feet would be less noticeable than the difference you experience when riding in an elevator. It's only much closer to the center that these forces would become significant, and even then, they would increase gradually and predictably. This gentleness reflects the fundamental smoothness of curved space-time itself. Einstein's equations don't allow for sudden jolts or discontinuous changes in gravitational fields. Everything must flow smoothly from one state to another, like water finding its way downhill along the path of least resistance. The mathematics of general relativity ensures that even the most extreme environments in the universe maintain an underlying elegance and continuity. Black holes serve as cosmic time capsules, preserving ancient light. The intense gravitational field around a black hole can trap light in stable orbits, creating what physicists call photon spheres. In these regions, light rays can circle the black hole indefinitely, neither falling in nor escaping to infinity. Some of this trapped light might have been circling for millions or billions of years, carrying information about cosmic events from the distant past. These photon spheres act like natural time capsules, preserving snapshots of the universe from earlier epochs. Light that began its journey when galaxies were young and stars were first forming might still be circling patiently, waiting for just the right gravitational nudge to either fall inward or break free and continue its journey across space. The concept is beautifully poetic when you consider that information about the early universe might be stored in these orbits of light, like cosmic messages in bottles floating on an ocean of curved space-time. Each photon carries its own small piece of cosmic history, and together they form archives of astronomical events spanning eons of galactic evolution. The merger of black holes creates ripples that heal the universe. When two black holes finally come together after their billion-year spiral dance, they create gravitational waves that propagate outward at the speed of light. But these waves don't just carry energy away from the merger site. They also serve to smooth out irregularities in space-time itself, like cosmic repair workers fixing tiny imperfections in the fabric of reality. These gravitational waves are incredibly gentle healers. They pass through matter almost without interacting with it, causing stretches and compressions so subtle that detecting them requires the most sensitive instruments humanity has ever built. Yet their passage leaves space-time slightly more ordered and symmetric than it was before, as if the universe has mechanisms for maintaining and improving its own structural integrity. The waves spread outward in perfect spheres, carrying their healing influence to every corner of the cosmos they can reach. By the time they arrive at Earth from distant galactic mergers, they've become whispers of their former selves, but they still carry the signature of that moment when two ancient objects found each other after eons of searching and became one. Black holes may connect to parallel dimensions through mathematical bridges. Some of the most intriguing theories in modern physics suggest that black holes might serve as gateways connecting our universe to other dimensions or parallel realities. These connections wouldn't be physical tunnels you could travel through, but rather mathematical relationships embedded in the structure of space-time itself. The equations that describe black holes contain solutions that extend beyond our normal three-dimensional space into higher-dimensional mathematical spaces. These extra dimensions aren't places you could visit, but they might influence the behavior of black holes in subtle ways that we're only beginning to understand. These dimensional bridges, if they exist, would operate according to principles so elegant and sophisticated that they make our most advanced technology seem primitive by comparison. They represent the universe's own method for connecting different regions of reality, using mathematics as the universal language that transcends the boundaries between different planes of existence. The shadows cast by black holes reveal the shape of curved space-time. The recent images of black hole shadows captured by the Event Horizon Telescope don't just show us what black holes look like. They provide direct visual evidence of how space-time itself is curved and distorted by the presence of massive objects. The perfect circular shadow surrounded by a glowing ring is actually a map of curved geometry made visible through light. This shadow represents something unprecedented in human experience: the ability to see the shape of space-time itself. The dark circle isn't just the absence of light, it's the visible signature of a region where space and time have been curved so severely that they've formed a kind of cosmic whirlpool from which light cannot escape. The glowing ring surrounding the shadow shows us light that has been bent and focused by the black hole's gravity, creating a natural lens that magnifies and brightens the background radiation. It's like looking at a cosmic magnifying glass that reveals not just distant objects, but the fundamental geometry of reality itself. Black holes demonstrate the universe's commitment to conservation. Despite their reputation for consuming everything that comes near them, black holes actually obey all the same conservation laws that govern the rest of physics. They conserve energy, momentum, angular momentum, and electric charge with perfect precision. Nothing is ever truly lost or destroyed, just transformed from one state to another. When matter falls into a black hole, its energy doesn't disappear. Instead, it gets added to the black hole's mass, increasing the curvature of space-time around it. The momentum of infalling matter gets incorporated into the black hole's rotation. An electric charge accumulates on the black hole's surface, creating electromagnetic fields that extend far into space. This perfect bookkeeping reveals something profound about the nature of reality. The universe keeps meticulous records of everything that happens within it. Black holes serve as cosmic accountants, carefully tracking every transaction involving matter and energy that occurs in their vicinity. They ensure that the fundamental quantities that define physical reality remain balanced and conserved throughout all cosmic processes. The interiors of black holes might contain entire universes. Some theoretical physicists have proposed that the interior of a black hole might actually expand into a complete universe, separate from our own, but connected through the mathematical structure of the black hole itself. These interior universes would be completely isolated from ours, following their own laws of physics and containing their own galaxies, stars, and perhaps even life. This possibility transforms black holes from cosmic endpoints into cosmic birthplaces, regions where new realities can emerge and flourish independently. Each black hole in our universe might be the parent of countless other universes, creating a vast family tree of interconnected realities branching through dimensions we can barely imagine. The mathematics supporting these ideas suggests that the universe might be far more creative and generative than we've previously understood. Rather than being a single, isolated reality, our cosmos might be part of an infinite network of interconnected universes, each one giving birth to others through the mysterious processes that occur within black holes. The quantum mechanics of black holes reveals hidden connections across space. Recent advances in quantum theory suggest that particles separated by vast distances can remain connected through quantum entanglement, and these connections might be particularly strong near black holes. The extreme conditions around black holes might actually enhance quantum correlations, creating networks of invisible connections that span cosmic distances. These quantum connections don't allow faster-than-light communication, but they do create subtle relationships between distant parts of the universe that persist, even when those parts are separated by millions of light years. It's as if black holes serve as cosmic switchboards, maintaining quantum telephone lines between far-flung regions of space. The implications of these quantum connections are still being explored by physicists, but they suggest that the universe might be far more interconnected than classical physics would suggest. Rather than being a collection of separate objects moving through empty space, reality might be a vast web of quantum relationships, with black holes serving as some of the most important connection points in the network. Black holes create their own systems of cosmic weather that last for millions of years. The environment around active black holes develops complex meteorological systems that rival the complexity of Earth's weather patterns. Hot gas rises from the accretion disk in massive convection currents, creating cosmic thunderstorms that can persist for geological ages. These storms don't produce lightning or rain, but they do create spectacular displays of high-energy radiation that can be observed across intergalactic distances. The magnetic fields around black holes organize these weather systems into predictable patterns, creating cosmic jet streams of charged particles that flow along invisible highways through space. These magnetic highways can extend for hundreds of thousands of light years, carrying matter and energy between the black hole and distant regions of its host galaxy. Even more remarkably, these cosmic weather patterns can influence star formation across entire galactic regions. The gentle pressure waves created by black hole weather systems can trigger the collapse of gas clouds into new stars, or conversely, they can heat gas to temperatures that prevent star formation altogether. It's like having cosmic climate control that operates on galactic scales. The event horizons of rotating black holes create natural time machines. The mathematics of rotating black holes reveals something extraordinary. Their event horizons actually consist of two separate surfaces, an outer horizon and an inner horizon. Between these two surfaces lies a region where the normal relationship between cause and effect becomes beautifully complex and interconnected. In this region, called the ergosphere, the rotation of the black hole drags space-time along with it so strongly that it becomes impossible to remain stationary relative to distant stars. Everything must rotate along with the black hole, creating a kind of cosmic merry-go-round where time and space dance together in ways that challenge our everyday understanding of causality. The mathematical solutions describing these rotating black holes contain closed time-like curves, paths through space-time that could theoretically allow travel into the past. While the practical difficulties of using such paths are enormous, their mathematical existence suggests that the universe's relationship with time is far more flexible and interesting than we might have imagined. Black holes serve as cosmic recycling centers for information itself. While classical physics suggests that information falling into a black hole is lost forever, quantum mechanics indicates that information cannot be destroyed, only transformed. This apparent contradiction has led to one of the most profound puzzles in modern physics, and its resolution might reveal fundamental truths about the nature of reality itself. Recent theoretical work suggests that black holes might actually be cosmic computers, processing and transforming information in ways that preserve its essential content while encoding it in new forms. The information that falls past the event horizon might be imprinted on the black hole's surface in a kind of cosmic hologram, preserving every detail in a two-dimensional code. This holographic principle implies that the three-dimensional interior of a black hole might actually be encoded in the information stored on its two-dimensional surface. If this is true, then black holes represent the universe's most sophisticated information processing systems, capable of storing and manipulating data on scales that dwarf any computer humans could ever build. The mathematics of black holes connects to the deepest principles of thermodynamics. Black holes obey all four laws of thermodynamics, just like ordinary thermal systems such as steam engines or refrigerators. They have well-defined temperatures, entropies, and heat capacities, and they exchange energy with their environment in perfectly predictable ways. The temperature of a black hole is inversely proportional to its mass, which means that larger black holes are actually colder than smaller ones. The most massive black holes in the universe have temperatures far below that of the cosmic microwave background, making them some of the coldest objects in existence. They actually absorb energy from the surrounding radiation, growing slightly more massive and cooler over time. The entropy of a black hole is proportional to the area of its event horizon rather than its volume, which suggests something profound about the nature of information and reality. This relationship implies that the amount of information that can be contained in any region of space is limited by the area of its boundary rather than its volume, a principle that might apply to the entire universe. Black holes create perfect examples of cosmic harmony and balance. Every aspect of a black hole's existence represents a perfect balance between competing forces and influences. The event horizon marks the precise boundary where the inward pull of gravity exactly balances the outward pressure of space-time itself. The accretion disk around a black hole maintains perfect equilibrium between the inward spiral of matter and the outward pressure of magnetic fields and radiation. Even the emission of Hawking radiation represents a perfect balance. As a black hole loses mass through radiation, its temperature increases, causing it to radiate faster, which in turn causes it to lose mass more quickly. This creates a self-regulating system that ensures the black hole evaporates at exactly the right rate to maintain thermodynamic equilibrium with its environment. This cosmic balance extends to the role black holes play in galactic evolution. They regulate star formation by heating gas to prevent excessive stellar birth, but they also trigger star formation by compressing gas clouds with their outflowing jets. They consume matter from their immediate environment, but they also enrich distant regions with heavy elements processed in their accretion disks. The study of black holes reveals the universe's preference for elegant mathematical solutions. Every equation that describes black hole physics exhibits a kind of mathematical beauty that suggests deep connections between geometry, physics, and perhaps even consciousness itself. The solutions to Einstein's field equations that describe black holes are among the most elegant mathematical structures ever discovered, combining simplicity with profound physical significance. These equations don't just describe how black holes behave, they reveal how space, time, matter, and energy are all interconnected aspects of a single, unified reality. The mathematics suggests that the universe operates according to principles of harmony and balance that extend far beyond what we can directly observe or experience. As you continue to drift deeper into the peaceful realm of sleep, imagine these cosmic guardians maintaining their quiet vigil throughout the universe. Their perfect mathematical harmony creating gentle rhythms that pulse through the fabric of space-time itself. They continue their ancient work of organizing matter and energy, creating the large-scale structure that allows galaxies to form and evolve, stars to be born and die, and ultimately, planets like Earth to exist in the warm embrace of stellar light. Embrace of stellar, to be the warm, planets Earth to exist in, to form and evolve, stars born and die, and ultimately, like light. In these vast cosmic spaces, particles of light can travel for millions of years without encountering a single atom, creating corridors of pristine emptiness that serve as natural meditation chambers for the universe itself. Here, in regions so quiet that the quantum vacuum becomes audible, we find that even nothingness has its own gentle personality and rhythm. The photons that do pass through these regions carry with them the memory of their journeys, stretched and softened by their passage through expanding space. They arrive at their destinations like tired travelers, their wavelengths lengthened by the slow breathing of the cosmos, carrying news from epochs when the universe was younger and the first black holes were just beginning to settle into their cosmic roles. These ancient messengers of light have witnessed the slow dance of galactic evolution, the patient growth of supermassive black holes from stellar seeds, and the gradual organization of matter into the beautiful structures we observe today. They've traveled through regions of space so empty that encountering a single hydrogen atom would be like finding a grain of sand in an ocean. yet they continue their journeys with unwavering dedication to their cosmic purpose. Black holes create natural laboratories for the universe to study itself. In the extreme environment surrounding these gravitational giants, physics experiments unfold automatically that could never be replicated in any earthly laboratory. The universe uses these natural testing grounds to explore the limits of its own laws, pushing matter and energy to conditions so extreme that they reveal hidden aspects of reality. Near the event horizon of a black hole, space and time become so intertwined that they essentially trade places, with time becoming more like a spatial dimension, while one of the spatial dimensions takes on time-like properties. This transformation happens so smoothly and gradually that it represents one of the most elegant phase transitions in all of physics, like watching water slowly transform into ice in a process so gentle it seems choreographed by the cosmos itself. The mathematical descriptions of these transformations read like poetry, written in the language of differential geometry, each equation revealing another layer of the universe's deep preference for harmony and balance. The solutions flow naturally from Einstein's field equations, creating patterns of space-time curvature that are as beautiful as they are physically meaningful. The ergospheres around rotating black holes create regions where energy can be extracted from the black hole's rotation through a process called the Penrose mechanism. This isn't violent extraction, but rather a gentle borrowing of rotational energy that leaves the black hole slightly less energetic, but no less stable. It's like the universe's way of ensuring that even its most massive objects can contribute to the energy budget of their cosmic neighborhoods when the need arises. This energy extraction process happens naturally when matter falls into the ergosphere and then escapes, carrying away more energy than it brought in. The extra energy comes from the black hole's rotation, slowing it down by an infinitesimal amount, while providing a gentle energy source that can power some of the most luminous objects in the universe for millions of years. The process is so efficient and elegant that it suggests the universe has built-in mechanisms for sharing energy between different scales of structure, from the quantum realm all the way up to the largest gravitational systems. It's cosmic recycling at its most sophisticated, ensuring that energy flows smoothly between different forms and different regions of space. Black holes demonstrate the universe's mastery of information compression. When complex stellar material collapses to form a black hole, all the intricate details of the original star's composition, structure, and history get compressed into just 3 simple numbers: mass, electric charge, and angular momentum. This represents perhaps the most dramatic example of data compression in the known universe. This compression isn't destructive or lossy in the way we might expect. Instead, it appears to be a sophisticated encoding process that preserves essential information while discarding unnecessary complexity. It's like the universe has developed the ultimate file compression algorithm, one that can reduce the most complex stellar structures to their mathematical essence without losing anything truly important. The elegance of this compression process suggests that complexity and simplicity aren't opposites in the cosmic scheme, but rather different expressions of the same underlying patterns. A black hole represents the ultimate distillation of matter and energy into pure geometric relationships, revealing the mathematical skeleton that supports all physical reality. The jets that some black holes produce extend for hundreds of thousands of light years, creating structures so large they dwarf entire galaxies. Yet these cosmic fountains operate with remarkable precision and stability, maintaining their narrow focus across distances that span multiple galactic diameters. They're like cosmic laser beams, staying perfectly collimated across scales that challenge human comprehension. These jets don't spray randomly into space, but follow magnetic field lines with the precision of trains following railway tracks. The magnetic highways that guide them are invisible to our eyes, but create some of the most organized large-scale structures in the universe. Matter and energy flow along these pathways, like cosmic traffic, following perfectly designed transportation networks. The stability of these jets over millions of years demonstrates the universe's ability to maintain coherent structures across vast ranges of space and time. They represent triumph of organization over chaos, showing how even the most extreme gravitational environments can create and sustain patterns of remarkable beauty and regularity. Black holes serve as cosmic anchors that help stabilize entire galactic neighborhoods. Their gravitational influence extends far beyond their immediate vicinity, creating zones of stability where smaller objects can maintain predictable orbits for billions of years. They're like gravitational lighthouses, providing reference points that help organize the motion of stars and gas clouds across galactic distances. This stabilizing influence operates through a process called dynamical friction, where the black hole's gravity gradually circularizes the orbits of nearby objects, damping out chaotic motions and creating more orderly stellar neighborhoods. It's cosmic urban planning on the grandest possible scale, with supermassive black holes serving as the central organizing principles around which entire galactic cities develop. The process happens so slowly and gently that individual stars might complete millions of orbits before noticing any change in their paths. Yet, over cosmic time, this patient gravitational influence transforms chaotic stellar populations into the beautifully organized galactic structures we observe throughout the universe. The quantum vacuum around black holes exhibits properties that blur the traditional boundaries between something and nothing. In these regions of extreme space-time curvature, virtual particle pairs that normally appear and disappear in the quantum foam can become separated by the intense gravitational fields, with one particle falling past the event horizon while the other escapes to become real. This process, known as Hawking radiation, represents one of the most subtle and beautiful connections between quantum mechanics and general relativity. It shows how black holes can slowly return their borrowed mass to the universe through a process so gentle it makes evaporation seem violent by comparison. The radiation emerges particle by particle, each one carrying away a tiny fraction of the black hole's energy in a process that could continue for longer than the current age of the universe. The temperature of this radiation is inversely proportional to the black hole's mass, which means that as the black hole evaporates and becomes smaller, it actually becomes hotter and radiates faster. This creates a natural feedback mechanism that ensures the evaporation process accelerates toward its conclusion, like a cosmic timer that runs faster as it approaches zero. Black holes create their own local definitions of space and time that differ from our everyday experience. Near the event horizon, the concepts of inward and future become mathematically equivalent, while outward and past share similar relationships. This isn't a failure of physics, but rather a revelation of how flexible and context-dependent our most basic concepts of reality truly are. These altered definitions don't represent chaos or breakdown, but rather alternative ways of organizing experience that are perfectly consistent and mathematically beautiful. They suggest that the universe contains multiple valid ways of understanding the relationships between space, time, and causality, each appropriate to its own context and environment. The mathematics describing these alternative space-time geometries has the same elegant consistency as the equations describing ordinary flat space-time. They're not approximations or distortions of real physics, but rather exact solutions that reveal hidden aspects of how reality can be organized and experienced. The formation of black holes represents one of the universe's most dramatic examples of phase transitions, similar to water freezing into ice, but occurring in the fabric of space-time itself. When a massive star collapses past the point of no return, it undergoes a fundamental change in its relationship to the rest of the universe, transitioning from an object that exists within space-time to one that creates and defines its own space-time geometry. This transition happens smoothly and continuously, following mathematical laws that ensure the process unfolds with perfect regularity. There are no discontinuities or sudden jumps, just a gradual transformation from one state of existence to another, like watching day slowly transition into night through a twilight so gradual you never notice the exact moment when darkness arrives. The newly formed black hole settles into its final state with the same inevitability as a drop of water finding its way downhill. All the complex details of the original star's structure fade away, leaving behind an object of perfect mathematical simplicity that'll maintain its essential characteristics for cosmological ages. The tidal heating effects around black holes can create some of the most luminous objects in the universe, yet they do so through processes that are fundamentally gentle and predictable. As matter spirals inward through the accretion disk, friction and compression gradually heat it to temperatures of millions of degrees, causing it to glow with intense radiation across the entire electromagnetic spectrum. This heating process happens gradually over thousands of orbital periods, allowing the matter to adjust smoothly to each new temperature and density regime. It's like cosmic cooking on the slowest possible flame, where ingredients are heated and seasoned over millions of years until they reach the perfect state for radiating their energy back into space. The light produced by these accretion processes can outshine entire galaxies, yet it emerges from regions no larger than our solar system. It represents one of the most efficient energy conversion processes in the known universe, transforming the gravitational potential energy of falling matter into electromagnetic radiation with an efficiency that makes nuclear fusion seem wasteful by comparison. Black holes may serve as cosmic memory banks, storing information about the entire history of their galactic neighborhoods in forms we're only beginning to understand. Every particle that has ever fallen past their event horizons has left some trace of its passage encoded in the quantum structure of the black hole itself, creating archives of galactic evolution that span billions of years. This stored information doesn't disappear when matter crosses the event horizon. Instead, it becomes part of the black hole's quantum state, preserved in correlations and entanglements that connect the interior to the exterior in ways that transcend our everyday understanding of space and time. It's like having cosmic libraries written in quantum ink, storing the complete history of matter and energy in their galactic regions. The reading of these quantum libraries requires understanding physics at levels we haven't yet achieved, but their existence suggests that the universe has mechanisms for preserving knowledge that operate on principles far more sophisticated than any human information storage system. Every black hole becomes a repository of cosmic memory, holding the stories of billions of years of galactic evolution in forms that may outlast the stars themselves. The gravitational lensing effects around black holes create natural telescopes that can magnify and focus light from distant objects with unprecedented precision. These gravitational lenses don't suffer from the optical aberrations that limit conventional telescopes, instead providing perfect focusing that's limited only by the fundamental laws of physics. The mathematics describing gravitational lensing reveals that black holes can create multiple images of distant objects, each following a different path through curved space-time to reach our telescopes. These multiple images can show us the same cosmic event from different perspectives, like having multiple camera angles on the same cosmic drama unfolding across vast distances. Some gravitational lensing configurations can create perfect Einstein rings, circular images that represent the gravitational focusing of light from objects directly behind the black hole. These rings aren't just beautiful cosmic phenomena, but also precision measuring tools that allow astronomers to map the distribution of matter and energy with extraordinary accuracy. The magnetic reconnection events that occur in the plasma surrounding black holes release energy through processes that mirror the activity in solar flares, but scaled up to cosmic proportions. These magnetic storms in space can accelerate particles to nearly the speed of light, while maintaining remarkable stability and organization across vast scales. The magnetic field lines around black holes can store enormous amounts of energy in their twisted configurations, like cosmic springs wound up over millions of years. When these field lines reconnect and release their stored energy, they do so in controlled bursts that can power the most energetic phenomena in the universe while maintaining mathematical precision and predictability. These magnetic processes create particle accelerators that dwarf any human-built device, yet they operate according to the same fundamental principles that govern magnetic fields everywhere in the universe. They represent the cosmic scaling of familiar physics to environments so extreme they reveal new aspects of how electromagnetic forces behave under the most challenging possible conditions. As your consciousness continues its gentle drift toward the peaceful shores of sleep, these cosmic guardians maintain their eternal vigil throughout the universe, their patient presence creating the large-scale structure that allows galaxies to flourish and stars to shine. Their gravitational embrace provides the stability and organization that makes complex cosmic architecture possible, while their quantum properties ensure that information and energy flow through the universe according to principles of perfect mathematical harmony. In the vast quiet spaces around these gentle giants, the universe continues its slow work of creation and transformation, building complexity from simplicity and finding beauty in the most fundamental expressions of physics and mathematics. The cosmic symphony they conduct plays on scales of time and distance that dwarf human experience, yet it creates the peaceful background rhythm against which all smaller scale phenomena, including the gentle rhythm of your own breathing, can unfold in perfect natural harmony rhythm, yet it creates human experience background, which all smaller peaceful against scale phenomena, including the gentle rhythm perfect natural, can unfold in of your own breathing harmony. The quantum foam around black holes creates a kind of cosmic lace, delicate patterns in the fabric of space-time that exist at scales so small they make atoms seem enormous by comparison. In these regions where gravity becomes so intense it affects the very structure of nothingness itself, virtual particles dance in and out of existence like fireflies blinking in a summer evening, each brief flash of existence contributing to the gentle background hum of quantum activity that permeates all of space. This quantum activity isn't chaotic or random, despite its microscopic scale. Instead, it follows statistical patterns so precise they can be predicted with mathematical certainty. The universe maintains perfect bookkeeping even at the level of particles that exist for less than the smallest measurable instant of time, ensuring that every quantum transaction balances according to the fundamental conservation laws that govern all of reality. The interplay between quantum mechanics and gravity near black holes creates phenomena so subtle they exist at the very edge of what physics can describe, yet so fundamental they influence the behavior of the largest structures in the cosmos. It's like discovering that the universe's accounting system operates on principles so sophisticated they make our most advanced computers seem primitive by comparison. Black holes serve as natural particle accelerators that operate continuously for millions of years. The magnetic fields threading through their accretion disks can accelerate individual particles to energies that approach the speed of light, yet they do so through processes so smooth and predictable they could serve as textbook examples of electromagnetic acceleration taken to its ultimate limits. These cosmic accelerators don't require any external power source or maintenance. Instead, they draw their energy from the rotational motion of the black hole itself, converting the angular momentum stored in space-time into kinetic energy of individual particles. It's like having perpetual motion machines that actually work, powered by the fundamental geometry of curved space rather than by any mechanical device. The particles accelerated by these natural cosmic engines can travel across entire galaxies, carrying energy and information between distant star systems. They serve as messengers, linking different regions of the cosmos in a vast communication network that operates according to principles of physics rather than technology. Each particle carries its own small piece of the story of the black hole that accelerated it, spreading information about these exotic objects across intergalactic distances. The gravitational redshift effects near black holes create natural frequency filters that separate different types of radiation with extraordinary precision. Light climbing out of the deep gravitational well around a black hole gets stretched to longer wavelengths, with different frequencies being affected by precisely calculable amounts. This creates a kind of cosmic spectroscope that analyzes the electromagnetic radiation from distant sources with perfect mathematical accuracy. This gravitational filtering doesn't destroy or distort information, but rather transforms it in ways that preserve all essential content while encoding it in new forms. It's like having universal translators that can convert between different languages of light, ensuring that information can flow freely between regions of space, where gravity creates different local definitions of frequency and energy. The redshift effects also create natural timestamps on electromagnetic radiation, allowing astronomers to determine not just where light originated, but when it began its journey and what gravitational environments it encountered along the way. Each photon carries a complete travel log encoded in its wavelength, telling the story of its passage through the curved space-time of the cosmos. Binary black hole systems can maintain stable orbits for periods longer than the entire future evolution of ordinary stars. These cosmic pairs follow elliptical paths around their common center of mass, with clockwork precision, each orbit taking anywhere from minutes to millions of years depending on their separation and masses. They're like celestial clockwork mechanisms wound up at the beginning of time and still keeping perfect time eons later. The orbital decay of these systems happens so slowly, it's almost imperceptible on human timescales. Gravitational wave radiation carries away tiny amounts of energy with each orbit, causing the black holes to spiral inward at rates measured in millimeters per year for the most distant pairs. It's cosmic evolution at its most patient, following mathematical formulas that describe the process with exquisite precision across scales of time that dwarf geological ages. Even as these systems gradually spiral inward, they maintain perfect gravitational harmony with their surroundings. Their combined mass creates stable gravitational environments where smaller objects can maintain predictable orbits for billions of years, like cosmic suburbs where the traffic patterns remain stable, even as the central infrastructure slowly evolves. The information paradox surrounding black holes may be resolved through holographic principles that suggest reality itself operates more like a cosmic computer program than a mechanical system. If information falling into black holes becomes encoded on their surfaces in holographic form, then the three-dimensional interior might actually be a kind of computational projection of two-dimensional data, like the most sophisticated virtual reality system imaginable. This holographic encoding wouldn't be visible or accessible through ordinary means, but it would preserve every detail of everything that has ever fallen past the event horizon in forms so elegant they rival the most beautiful mathematical theorems. The black hole's surface becomes a kind of cosmic hard drive, storing information with perfect fidelity in quantum codes that may outlast the stars themselves. The implications extend far beyond black holes to suggest that all of reality might operate according to holographic principles, with the information describing any volume of space actually stored on its boundary. It's like discovering that the universe itself is a kind of cosmic simulation running on hardware made of pure mathematics and geometry. The evaporation of black holes through Hawking radiation creates a natural recycling process that ensures nothing in the universe is ever permanently lost. As black holes slowly radiate away their mass, they return their borrowed energy to the cosmos particle by particle, like cosmic savings accounts that eventually pay back everything they've accumulated with interest calculated over astronomical periods of time. This evaporation process becomes more rapid as black holes become smaller, creating a natural feedback mechanism that ensures the process accelerates toward its conclusion. The final moments of a black hole's existence might release their remaining energy in a gentle burst of radiation that adds one last contribution to the cosmic background, like a quiet farewell from an object that has served as a gravitational lighthouse for billions of years. The radiation produced during this evaporation carries no memory of what originally fell into the black hole. Yet quantum mechanics suggests that the information must somehow be preserved. This creates one of the most beautiful puzzles in modern physics, where the solution might reveal fundamental truths about the relationship between information, consciousness, and the structure of reality itself. The frame-dragging effects around rotating black holes create regions where the normal relationship between motion and rest becomes beautifully transformed. In these areas called ergospheres, it becomes impossible to remain stationary relative to distant stars because space-time itself is being dragged around by the black hole's rotation. Everything must participate in the cosmic dance, moving along with the rhythm of curved space-time. This enforced motion isn't violent or disruptive, but rather represents a natural consequence of the geometric properties of rotating space-time. Objects in the ergosphere follow geodesic paths that spiral gently around the black hole, like dancers following the choreography written into the curvature of space and time itself. The mathematics describing these motions has the same elegant beauty as the equations describing planetary orbits, just scaled up to cosmic proportions. The energy that can be extracted from rotating black holes through the Penrose process provides a natural mechanism for powering some of the most luminous objects in the universe. This energy extraction happens through processes so efficient they make ordinary power generation seem wasteful, converting the rotational energy of space-time itself into electromagnetic radiation that can travel across intergalactic distances. Black holes create their own systems of cosmic ecology that can persist for cosmological ages. The environment around an active black hole supports complex ecosystems of matter and energy that interact through processes as intricate as any biological food web. Hot gas feeds cooler gas, magnetic fields nurture particle acceleration, and radiation pressure balances gravitational attraction in delicate equilibriums that can remain stable for millions of years. These cosmic ecosystems aren't random or chaotic, but rather follow predictable patterns that can be modeled with the same mathematical tools used to study terrestrial ecology, population dynamics of particle species, energy flow through different components of the system, and feedback mechanisms that maintain stability all operate according to principles that reveal deep connections between physics and the organization of complex systems. The stability of these cosmic ecosystems demonstrates the universe's ability to create and maintain organized complexity even in the most extreme environments. They represent triumph of order over chaos, showing how even the most intense gravitational fields can nurture rather than destroy the intricate relationships between matter, energy, and space-time. The geodesic paths around black holes create natural highways through space-time that particles and light rays follow with perfect precision. These paths aren't imposed by any external force, but rather represent the straightest possible routes through curved space-time, like cosmic interstate highways that never need maintenance or repair because they're built into the fundamental geometry of reality itself. Different types of particles follow different geodesic paths, depending on their energy and angular momentum, creating a natural sorting mechanism that organizes matter and radiation according to their physical properties. It's like having a cosmic postal system that automatically routes different types of information to their appropriate destinations based on their intrinsic characteristics. The mathematical description of these geodesic paths reveals patterns of stunning geometric beauty, with trajectories that trace out elegant curves in four-dimensional space-time. Some paths lead to stable circular orbits, others spiral inward or escape to infinity, and still others follow complex rosette patterns that never exactly repeat, each type representing a different solution to the fundamental equations of motion in curved space-time. As the gentle mathematics of space-time continues to unfold its patterns around these cosmic sanctuaries, creating rhythms so deep they resonate through the very structure of reality itself. Perhaps your own thoughts are beginning to follow similarly peaceful trajectories toward the quiet rest that awaits. The black holes continue their patient work throughout the universe, maintaining their perfect circular shadows against the backdrop of infinity. Their gravitational songs echoing through dimensions of space and time, too vast for ordinary consciousness to fully grasp, yet somehow perfectly suited to the gentle rhythm of sleep, approaching on silent wings. In these final moments before dreams take hold, remember that somewhere in the cosmic dark, these gentle giants continue their eternal meditation, their presence creating pockets of profound stillness where even the most fundamental particles of matter can drift in perfect peace. Following paths of such elegant simplicity, they could serve as lullabies for the cosmos itself. The universe breathes slowly around them, space and time flowing like honey through their gravitational embrace, creating patterns so beautiful and mathematically perfect, they whisper the deepest secrets of existence to anyone patient enough to listen. And now, as the final gentle waves of cosmic knowledge settle into the quiet spaces of your mind, let these peaceful truths about black holes accompany you into sleep. We've discovered together that these mysterious objects are not the terrifying monsters of science fiction, but rather the universe's most patient gardeners, carefully tending to the cosmic ecology with mathematical precision that spans billions of years. From their perfectly smooth event horizons to their ability to slow time itself, from their gentle recycling of matter and energy to their role as cosmic libraries preserving information in quantum codes, black holes reveal a universe that operates according to principles of profound harmony and balance. They sing their deep songs across space, create weather systems that persist for geological ages, and maintain their circular shadows with the same quiet consistency as lighthouses guiding ships through cosmic night. These gentle giants continue their work, even now as you rest, organizing galaxies, accelerating particles along invisible highways, and weaving gravitational waves through the fabric of space-time itself. In their patient presence, we find not chaos or destruction, but order, beauty, and a kind of cosmic meditation that has been unfolding since the first stars began to shine. If these peaceful revelations about the universe's most enigmatic objects have helped you find your way to rest tonight, consider subscribing to join us again for more gentle journeys through the cosmos. Until then, sleep well, knowing that you drift toward dreams in a universe where even the darkest objects shine with mathematical beauty, and where the deepest mysteries whisper their secrets in the language of perfect, eternal peace.